All right, so there'll be a homework due. On Monday at 7 a.m. All right, that homework will focus on colligative properties, which is what we're going to be talking about today. There is a quiz next Friday. And I'm available the regular times during the week. Next week, I'll go ahead and I'll list them on Monday. If you want help on anything over the weekend, feel free to send me an email. I do check my email a couple times a day. You might actually get lucky and I might be on my computer at the time. Okay, if I am, I'm happy to help. But if you have questions, please feel free to contact me. Questions on where we are, what we're doing? All right. Then last time we're going to be talking about the colligative properties today. And colligative properties are properties that depend on the number of particles in solution. So colligative properties depend on number of particles in solution. So a particle could be a molecule, it could be an ion. Okay, that's what I'm saying particles because I want to be general for everything. And so that means our Van 't Hoff factors become important. I think for this class, we didn't even get started on Van 't Hoff factors, so let's go ahead and talk about that. So what are Van 't Hoff factors? But this is a table of Van 't Hoff factors here. And these are things that are experimentally determined. So up to now, what we've done is we've talked about, let's say we have sodium chloride, and it's a solid, and it goes into solution. I've talked about it like it goes into solution 100%. In other words, we got sodium chloride in your ions, and it's going to break up absolutely 100% when it goes into solution. That's not really the case. Some of these they're attracted to each other, they have opposite charges. And so the effective number of particles is mostly this, maybe a little bit of, it's not solid, but maybe a little of them associated, so they act like one particle. And that's important in a world where the number of particles matter. So we've got this experimentally determined factor that we need to take into account. And so for sodium chloride, that factor is 1.8, right? So what that means is, I'm doing the math in my head, that 90% of them about 90% of them look like this, okay? But really, the ones where they're together count, so the algebra to figure out exactly what it is complex. What we're just concerned with is how many particles are made, so we can do our colligative properties. How many particles total? We don't need to know how many sodium pluses and how many sodium chlorides for the context of this class. So let's say 6.0 millimolar sodium chloride dissolves. So I can give you grams, you can calculate moles. We're going to skip that part, but dissolves into solution. Or let's not even say dissolves. Let's say I have a 6 millimolar sodium chloride solution. I like that better. Okay. What is the molarity of particles in that solution? All right, so if sodium chloride were ideal, this term of ideal means it doesn't, ideal is like it ignores the real world. There are things that happen in the real world. So there's a number of assumptions we can make in chemistry, and often they're very correct. They're correct, or they're pretty close to correct, and they make calculations a lot simpler. So often we talk about ideal gases, right? Ideal gases, the particles aren't attracted to each other and they have no volume, which isn't exactly true, but close enough. Same sort of thing here. So I have 6.0 millimolar sodium chloride. Millimolar is just like milliliters, right? I asked, what's the molarity of the solute particles in that solution? Oh, whoops. Anyway, I'm going to have to do a conversion there. All right, but that's fine. And I'm going to take that times the Van 't Hoff factor. If this was ideal, it would go from 6 millimolar to 12 millimolar because each sodium chloride would become 2 particles, right? Okay, but it's not ideal, so we're going to look our number up on the table. It actually becomes 1.8 particles. All right, and so then 1.8 times 6, I feel like I should be able to do that in my head, but that's going to be 10.8 millimolar. I did ask for the problem in millimolar, right? How many millimoles in a mole? 1,000, right. So 10.8 millimolar. If I have 1,000 millimolar, that's equal to 1 molar. Okay, millimolar cancels millimolar, and that's going to give me 0.0108 molar. And I had 2 significant figures, so 0.011 molar would be more correct with significant figures, right? Questions? You see where the Van Hoff factor comes in terms of the number of particles? Right now it's a little abstract. Who cares, right? Hopefully you'll care in a minute. All right, one reason that we care is that the number of particles in solution determines where water moves. Water will actually move from where there are fewer particles in solution to more particles in solution. So here's an example from your book. This is showing a cell. So we have the inside of the cell here. We have a lipid bilayer, which has been really lazily drawn here. It doesn't look like that. They come together like this. You've seen it looks like what it looks like in all your biology textbooks. Okay. But we have a lipid bilayer close enough, and then we have particles outside the cell. The way this is drawn, it looks to me like there's about the same number of particles outside as inside. All right, and if we think about particles, I mean, the water are particles too. Okay, but the water is a solvent in this case. So the solvent, we don't think about the particles. But if we look inside with 1, 2, 3, 4 particles, if we look outside 1, 2, 3, 4, at least in our view, right? But looking at those, the concentration looks about the same to me. However, if I had a situation where I had a lot more particles inside, let me go ahead and draw some. Let's say I have another one here, and another one here, and another one here. As is often the case, right, a cell isn't necessarily going to have the same number of particles outside as inside. Then what's going to happen is the water is going to want to move to where there are more particles. That's called osmotic pressure. Okay, and it's important in living systems. So let's say osmotic pressure. Okay. The solvent will move from a region with fewer solute particles to a region with more solute particles. Okay, and what we're talking about here is concentrations, right? I say fewer and more, but what I mean is less concentrated to more concentrated. Questions so far? Okay. All right, if you want to we're used to things moving in terms of diffusion from where things are, so water's moving from where things are less to more, right? We're used to things in diffusion. We've got a bunch here and not many here, and they move out, right? So from the perspective of the water, though, we're not violating that rule we talk about. We have if I have more particles in here, okay, I have less water because the particles take up space. And so water is moving from where there's more water to less water. You can think about it either way. Either way works in terms of a model for predicting what's going to happen. Questions? Conceptually? All right. So what does that mean? Well, you can get some pretty substantial effects here. If I have a beaker over here where I have a bunch of salt water, and I have a beaker over here that's pure water, and I have a semi-permeable membrane here. So a membrane that's only going to let water pass. It's not going to let the sodium or chlorides pass. What's going to happen is the water is going to move from this side to where there's more solute particles, from less solute particles to more solute particles. And so what you would see over time is there would be, this would push this way, okay? And then the water would raise up on one side. All right. And I had a good question last time, so would this keep moving until there was the concentration of solute particles was the same? Well, it can't because there are no solute particles over here, right? So what happens is the water keeps moving. We have this thing called osmotic pressure. It's going to keep moving until the osmotic pressure, in other words, the pressure of water trying to move over to the left container here, is equal to the pressure of the water as you raise it up higher. That height, the gravity pressure, pushes down. Okay, so that's what our osmotic pressure is. Questions? Okay, so this becomes really important in biology. So those of you who are pre-health, and by the way, if you're pre-health and you are not on the pre-health group mailing list, you should email me and I will make sure you get on it, okay? I'm no longer a pre-health advisor, but I used to be. If you're not on it, please write down to email me, and I'll get you on that pre-health list, mailing list. We take red blood cells. Red blood cells do not have the ability to pump water, okay? And so if you put red blood cells in an environment where there are more solutes inside the red blood cell than outside, or vice versa, they're in trouble. They have trouble with that. I used to do research as an undergraduate when I was working with blood. We were studying lupus, and so we had blood from people that had lupus, and then we need control blood, and so we do control blood from ourselves, right? This is back in the old days. So I would sometimes go to my research advisor, Dr. Lundquist, and I would draw blood from him. And I remember once I messed up and I got my solutions wrong, so that there was too much or not enough salts outside of the red blood cells, and the red blood cells all blew up. What happens here? I can't see blood. You can't. I mean, you see blood, but see blood in the tube, you can't see through it, right? But you blow up all those red blood cells, now suddenly it's a solution, and you actually can see through it. It's interesting. Anyway, so then I had to go back for more blood, but he wasn't pleased. But anyway, so what we've got here is we have some terms that you'll know in biology. I'm going to give you the terms. I'm not making you responsible for them because this is not a biology class, right? Take biochemistry, you'll be responsible for them. But an isotonic solution is a solution that has the same number and same concentration of particles outside as it does inside the cell. Okay, and then water moves back and forth across the membrane, but it doesn't go in or out. There's no net movement. All right, and so if you look at those cells, and your book has a nice picture, it's a cartoon, but it doesn't actually have any electron micrographs of it. Here we've got the red blood cells where you have the same concentrations of particles outside as inside. Nice little red blood cells. However, if it turns out you have more particles inside the cell than outside, so I drop my red blood cells in distilled water, let's say, water is going to move into the cells and they're going to expand. You see how this one's like a ball? That one's expanded as well. And they will actually expand until they blow up. We don't have any, that's hemolysis. We don't have any of that here unless these are pieces of a blown up red blood cell right there. If instead what I have is I have more salt outside, so let's say I took my red blood cell, I dropped it into salt water, what's going to happen is water's going to rush out of the red blood cell, and this is called crenulation, but what it does is it actually, they scrunch up, right? All right, so it's important. If you're doing research, if you're thinking about these things, your red blood cells in your body are designed to have the same number of particles inside as outside in the blood. Okay, they have to work that way. So your blood's maintained so you don't blow up your red blood cells. So this concept of osmotic pressure is important, and it can cause your cells to blow up, or it can cause cells to scrunch. Let's go ahead and try let me introduce the problem. Let me introduce the formula, and then let's do a problem. So osmotic pressure gets a big pi is equal to the Van't Hoff factor, right? That's going to help us figure out how many particles we have, times the molarity, times the ideal gas constant. Okay, it's going to be a different form, times the temperature in Kelvin. So let's go ahead and label what all these are. This is the temperature in Kelvin. This is the ideal gas constant. And the form we're going to use for this is going to be this form, 821 atmosphere liters per mole Kelvin. It's actually the same constant as this, 8.314 joules per mole Kelvin. Okay, but if we, if we use this form, so this is just a unit conversion thing. Okay, getting between one of these, they mean the same thing. But if we use this form in this equation, it's going to give us a pressure in atmospheres after everything cancels. So that's why we're using this one. We want a pressure, otherwise we get joule liters. Yeah, joule liters is a pressure. That's a weird pressure. But it clearly is. It has to be a pressure. Okay, so that's going to be that. This is molarity. This is our Van't Hoff factor. Anybody take German? Why don't I capitalize Van't? Must mean something. It must be. It's either a weird part of a name or it's that it isn't part of the name. And then this is our osmotic pressure. All right, so let's go down here and look at this. Let's do a different one than I did in the last class. Let's do this one. Okay. We'll go ahead and do this one. What we're going to do is we're going to use the Van't Hoff factors above to calculate the osmotic pressure here. Let's go ahead and look up the Van't Hoff factor. So this is KBr. So potassium bromide is 1.8. You see that? So I'm just going to look it up there and I'll bring it down here and I'll just say I equals 1.8. And then I'm going to remind you that this is what our equation, I'm going to actually remind you what, here, I'll say, I can get this all on the same screen, I bet. There. Go ahead and solve that. What are there units for the Van't Hoff factor? There are. That's a great question. Let's go, and I should have included them. What does it say they are? Oh. Nope. There are no units. So we can cancel our units in the end and see if that's right. Right? Call me over if you're having problems with this. But it is. Okay, thank you. Maybe 15 more seconds. Yes.
So what is this technically applicable to any sort of semi-permeable membrane? Because I know that certain parts of like the cell membrane have more aquaporins than others and stuff like that. Like it's different concentrations. So is it always going to be applicable, or is there going to be some sort of like additional thing that goes with that?
Okay, so that's a good question. So does the membrane matter? And it does matter. So we're talking about cells, maybe or maybe not, right? I'm sure you can get semi-permeable membranes that don't let water through, but let other things through. So I think it would matter depending on the membrane, but I think for all cells, water can leak through. I'm not aware of I'm not aware of a membrane where a biological membrane where water isn't getting through in some way or shape or form, right? And you're talking about aquaporins, you're talking about actual channels that are designed to let water through. But I don't know of a cell membrane where that you don't have the ability for water to pass. Other things are different. So if we talk about the mitochondria, sorry, I've been distracted. We have to have a segue now. So if we're talking about the mitochondria, don't apologize to me. You need to apologize to the rest of the class. No, I'm sorry. I shouldn't do that. But if we talk about the mitochondrial membrane, okay, mitochondria. What do you guys know about mitochondria? Who knows it? Powerhouse of the cell, right? Okay, it's making ATP, and where it makes ATP is it makes it across using this membrane. So what happens is you get a lot of proton, you get a lot of H plus here, and then you let it through and use that to make ATP. So if you look at the two membranes for the mitochondria, we've got the inner membrane and the outer membrane. This one is not permeable. Permeable to H plus, okay? And this one is permeable to H plus. And a lot of other stuff. It's permeable to fairly big stuff. So membrane is different. Different membranes do different things. Can I answer it?
Sort of.
Okay. All right. So let's go ahead and have me solve this. I'll get back to on task here. So we're doing KBr, right? We've got a concentration of KBr of 0.1 molar. By the way, your blood is about 0.150 molar sodium chloride. Okay, so most of that's about so that'd be about 0.3 molar particles, right? Because it mostly dissociates, something close to that. And that's most of the particles in your blood. All right, so we can come, so this is almost, if this was in a cell or in your blood, this would be almost doubling the amount of particles, or 2/3 again. We'll just see how much pressure we get out of that. All right, so we've got our temperature is 273 Kelvin. I'm looking just up at the equation now. Our R is 0.0821 atmosphere liters per, let me do that better. I want to cancel my units. So we're going to go ahead and we're going to go 273 Kelvin. We've got 0.0821 atmosphere times liters over mole times Kelvin. All right, times my molarity was 0.100 moles per liter. I'm going to go ahead and write moles per liter for molarity because I want to cancel those units. And then I've got my Van Hoff factor for KBr, which was 1.8. Right, that makes sense? I'll go ahead and put this all into my calculator. If I put it in my calculator, what'd you guys get? 4.03 atmospheres, right? Moles cancels with moles, kelvins with kelvins, liters with liters. I'm left with this poorly written atmospheres there. Okay, we're under 1 atmosphere of pressure right now. All right, so imagine it being 5 atmospheres of pressure. Not that you can imagine that. I'm trying to think of how deep you have to be. I think how deep you have to be in a swimming pool to be under 2 atmospheres of pressure. Anybody know? Okay, I'll figure it out for some other example. But that's a lot of pressure. Pressure in a pressure cooker is 2 atmospheres. We're talking about 4 more above what we're under. All right, so that'll blow up a cell really easily. Cells can't handle that. So the osmotic pressure can be a really big thing. Questions? All right, let's go ahead and move on. We're going to go talk about freezing point depression. All right, freezing point depression. So adding solutes to a solution, or to a solvent, let's say to a solution, will cause the freezing point to go down. All right, so it's freezing point depression. It will always go down. The equations I give you are not going to automatically tell you that, okay? Freezing point depression and boiling point elevation are really the same equation with some different constants you look up, all right? And they don't, and it doesn't come out that it's a negative number on freezing point depression. You need to remember to lower the freezing point. Does that make sense? It always goes down. So we can look at this sort of thing, and we have some experience with this, right? So over the last week, they've been throwing salt on the road, right, and things like that. Well, what happens when they throw salt on the road? Well, if we're going to throw salt and it's actually sodium chloride, and it doesn't need to be sodium chloride because you can do other salts and get more of an effect. But if you throw sodium chloride on the road, it dissolves into the ice. It lowers the freezing point of the ice, and if the freezing point is now -5 and the temperature is -3, now that ice is going to melt, okay? And some of the ice will just melt anyway, because if its temperature is here, right, the temperature is actually, temperature is here, and you lower the freezing point, some of it melts, it absorbs that heat of melting, and it becomes colder. That makes sense. So this is how, has anybody ever made ice cream where you have ice around your container and you throw salt in it and it makes it extra cold? Well, what's going on is I have ice. That ice is at probably 0 degrees Celsius around the container. I throw my salt in there. What happens is because I've dropped the freezing point, some of the ice melts. When it melts, it absorbs heat from your ice cream that you're trying to make, right? It absorbs heat from that, and so it gets cooler. All right, so lots of ways to use this sort of thing. Our equation for this goes as follows. We have a freezing point, we have a freezing point depression, so a change in temperature for freezing, and that's going to be equal to the Van Hoff factor. Once again, the number of particles matters. It's a colligative property times the molality. Remember, this is the one with the kilograms of solvent instead of liters of solution, times some constant we look up that's different for each solvent. So this is going to be freezing, and so this is constant that is different for each solvent. This here is our molality. This is our Van Hoff factor. And this is our freezing point depression. All right, and the factors we look up, none of these things are going to be negative, right? Which is good for me today because I didn't get as much sleep as I wanted last night. I'm really bad with dropping negatives. But there are no negatives today. So let's go ahead and do a problem with that. Here is a table. Here's a table with a mess of constants, okay, that are for these sorts of things, and we can use that to try and solve this problem. I will rewrite our equation down here. So let's go ahead and try to do this problem for freezing point depression. Actually, let's do the next one. I did that one last class, and we didn't get very, very big differences. Okay. So my equation here, let's go ahead and pull our constants so I can roll the table off the page here. So solution, we need to get the freezing point, or the freezing point. Let's get the freezing point for this much dichlorobenzene, 2.38 grams of dichlorobenzene in 500 milliliters of ethyl acetate. And then it gave me the density for ethyl acetate. Yeah, we'll do it. Okay, so what I want to do is I want to look up my constant for ethyl acetate. It's right here. All right, so my K freezing is going to be equal to 2.51 degrees Celsius per molal. Guys with me? All right, so now I want to remind you, we're going to pull this down so we get ourselves some space, and then I want to remind you that our equation is that the freezing point depression is equal to the Van't Hoff factor times, we're going to have to go look that up, times the molality times this Kf thing, okay? So let's take a second here. We need to look up our Van't Hoff factor for dichlorobenzene, right? What kind of compound, when you look at dichlorobenzene, what kind of compound does it look like? Ionic?
Oh, organic.
Well, it's an organic, yes. And it's not, it's molecular. It's not ionic, okay? The way it's written. Although you might have said, well, the CH4 might be an ion, a positive ion or something, but it's not. So this is molecular. So it is a non-electrolyte. What's the Van't Hoff factor going to be for a non-electrolyte? And if you read fast, the solutes are non-electrolytes in each case. So what's the Van't Hoff factor? Van't Hoff factor tells me when I dissolve something how many extra particles I get, right? I take it times when I dissolve it. If it's a non-electrolyte, does it split up into things in solution? No. So what's my Van't Hoff factor? 1. Okay. So we don't need to look up our Van't Hoff factor. But we are going to need to do some conversions here. So this is the tough part of this problem, right? I need to get the molality. Molality, as you remember, is moles divided by kilograms of solvent. And so I need to take my 500 milliliters and my density and then turn that into kilograms, right? So how am I going to do that? I have 500 milliliters of ethyl acetate, right? And if I have, how do I use the density? I'm going to use the density as a conversion factor here to get from milliliters to grams. What goes on the bottom? Milliliters. How many milliliters? 1, yeah. So this tells me if I look at my density here, if I have 1 milliliter, then I have 0.902 grams of ethyl acetate. That makes sense what I just did there? All right, and milliliter is going to cancel with milliliters. And then I need to use the formula weight to turn this into moles, right? Or the molecular mass to turn this into moles. So I'll have to calculate that. So I've got 6 carbons, right? Carbon is 12.01 grams per mole. I've got four hydrogens. That's 1.01 grams. I have 2 chlorines. I don't have one. 35.45. I'll have to memorize that so I can be more impressive in the future. So 12.01. 6 times that plus 4 times 1.01 plus 2 times 35.45. I got 147 even. Anybody else get that? 1.46 point what? 6. Anybody else? You dropped it. Oh, well, there you go. Go you. All right, 147 is close enough, though. I'm going to go with my 147. All right, so we've got 147 grams. I feel like I should have that many sig. We'll do that many sig figs since we were doing an adding sort of thing. Equals 1 mole, right? So over here I say 147.00 grams is equal to 1 mole. And it's EA and EA again, ethyl acetate, both cases. Grams goes with the grams, and now I'm ready. I'm going to get moles out. All right. And so I'm going to go 3 significant figures, 307 moles ethyl acetate, dichloroben, or no, ethyl acetate. We're trying to figure out. I'm sorry, I got all confused. We want kilograms of the solvent, right? Not moles of the solvent. Okay, let's back up. Just did a whole bunch of work I didn't need to do.
You still need the 147 because you have to convert the grams of the C6H.
That was really bad. You guys got to stop me when I'm doing that kind of stuff, right? I was just testing. All right, so let's go ahead and fix that. All right, so we need kilograms here, right? How do I go from grams to kilograms? I got 1,000, right? What goes on the bottom? Yep, so 1,000 grams is equal to 1 kilogram. All right, this will be the amount of solvent, or the kilograms of solvent. So 500 times 0.902 divided by 1,000. I told you I was sleepy today. 451 kilograms. All right, that's going to go on the bottom for our molal, right? That's this bit. Now, we did have a 147 that grams is equal to 1 mole, but that was of the dichlorobenzene. Dichlorobenzene. We'll abbreviate it like that. So I have 2.38 grams of dichlorobenzene. How do I use this as a conversion factor? What goes on the bottom? 147 grams goes on the bottom. 147 grams of dichlorobenzene is equal to 1 mole of dichlorobenzene. All right, so we have 2.38 divided by 147, 0.0162. Okay, moles of dichlorobenzene. All right, we're finally ready to do this, right? Remember we had this. Remember way back when we had this equation that we were trying to solve something for. We need to look up that K freezing. Oh, we did. It's right here, right? All right, so let's go ahead. I'm going to do this one in green down here. So our Van't Hoff factor we said was 1, right? Because it's a non-electrolyte. Our molality is going to be this 0.0162 moles over 0.451 kilograms times what we've got then is that constant. This is constant right there, goes here. So that's going to be 2.51 degrees Celsius molal, or yes, per molal. Okay. And that's going to give us our answer here in terms of how much the freezing point goes down. And then we'll have to subtract it from the freezing point. All right, so okay, and so what I got out of that was I got a 0.0902 is how much degrees Celsius, right? Kilograms is going to cancel with, kilograms per moles per kilogram is molal, so those cancel, and I'm just left with degrees Celsius. All right, that's how much it goes down. So we're asked for the actual freezing point. Remember, it's freezing point depression. So if we go up here to ethyl acetate, we see its freezing point is negative 83.8. So we'd have negative 83.8 degrees Celsius. That's the freezing point, minus the depression, which is 0.0902 degrees Celsius. I'm going to ignore my significant figures here because otherwise I'll lose my change. Actually, this problem is weird. They didn't write a really good problem here in that your stuff's going to get it would all round to nothing. But 83.8902 degrees Celsius. So it went down a little bit, like 1/10 of a degree. Questions? Okay. Then let's go on. We've got 8 minutes left, and I want to cover boiling point elevation. It's really the same thing, okay? So what this says is solution boiling points increase when you add more, the concentration of solutes increase. I'm going to actually not say solids, I'm going to say concentration of particles, right? Because it's all about particles. So in other words, we're not doing a problem like this, but if I had a solution with water and I was throwing salt in, I was throwing sugar in, okay? And I was throwing some protein in, okay? On top of that, I'm going to use fudge as an example. You throw a lot of things into fudge, all right? All of those things make the boiling point go up. All right, and that's an example. This is probably an example that isn't going to work for many of you because many of you, I don't know how many of you make fudge, but how many people make fudge on the stove top? Put it on the stove top, you're heating it. Nobody? Two in the last class? Your moms make you cook? Well, it's sexist. Maybe it's your dad's making you cook now. You don't know. But we're okay. Well, when you're cooking fudge, I make fudge. So if you're cooking fudge, what you do is you're cooking it and making. What the thing is about making fudge is that it's got a bunch of sugar in it, but you want to concentrate that sugar. So you make a solution in water, essentially, it has sugar in it, and then you're boiling the water off until the sugar becomes more concentrated. If you boil off too much, it all just crashes out, and you get lumpy, breaky fudge, right? It's not got that smooth texture to it. So you got to catch it at the right point. And how do you know where the right point is? You have a thermometer in it, and you're watching the temperature rise. The boiling point is increasing as the sugar becomes more concentrated. Does that make sense? I'm boiling off water, so the sugar is becoming more concentrated. So that's an example of where you might use a boiling point elevation. There are other things as well. The equation for boiling point elevation is the same equation we had above, except we're going to grab our constants from different places on the table. So we've got the Van't Hoff factor times the molality times the constant we pull from the table, the boiling point constant from whatever solvent we're talking about. Okay, so we could do that for, we don't have a lot of time. I'm going to make up a problem. I don't like these problems where the temperature doesn't change much, okay? So I have a solution I make a solution, let's say, by adding, I was going to do a fudgy solution by adding sugar, but let's do something where we actually have a Van't Hoff factor where things break up. So I make a solution by adding, I'm going to add sodium chloride. Let's add a lot. Let's add 501 grams of sodium chloride to, and let's go ahead and make it 1 let's make sure we really have a change. 0.085 kilograms, it'll save us that conversion of water. What is the boiling point of this solution? Okay, so that's a lot of sodium chloride. Well, maybe about that much, fist size, not handful, fist size, but all right, so I'm going to go ahead and do that. I need my equation here. I remember I go look up my Van't Hoff factor from up above. If you remember from earlier, this Van't Hoff factor was 1.8 for sodium chloride. You may not, you don't need to memorize them. I just remember it. So we won't bother scrolling back up. So then we're going to go ahead and do this for the solution. I need to get the molality, which means I need the moles of sodium chloride, right? Anybody get us the molecular mass of sodium chloride yet? 58.44 grams equals 1 mole. Okay, right? Where it's grams per mole there, but that's the same as saying 58.44 grams equals 1 mole. So we have 501 grams of sodium chloride. I'm going to use my molecular mass. How do I use this to get moles? The molar mass on the bottom. The 588.44 goes with the grams. Now cancel is equal to 1 mole. Grams cancels with grams, and then I get something like 9 or 8 or something. Did somebody else do it already? 8.57. Okay. Moles, sodium chloride, lots of moles. Okay. So we get lots of moles. We'll hopefully get a big change here. And so I'm going to go ahead and I'm going to take my equation down here. I've got 1.8 times the molality is 8.57 moles. That's divided by, I've got 0.805 kilograms of water. This might actually be too much sodium chloride to go into water, but we're going to pretend that it does, okay? And then we need this boiling point elevation constant from our table, right? We looked that one up. So for water, our boiling point elevation is it's a measly 0.51. We're still going to get a good change. 0.51, and that's going to be degrees per molal. Remember, moles over kilograms is molal, so this is a molal, that's a molal, they cancel, and I'm going to get degrees Celsius. Put my calculator, 1.8 times 8.57 times 0.51 divided by 0.805. Anybody else get 9.58? Okay, so I've got our boiling point elevation is 9.5. We're going to call it, well, we got 1.8 there, so I'm going to call it 9.6, okay, degrees Celsius. So where does water boil when it's pure? Yep, water boils when it's pure at 100 degrees Celsius, plus its boiling point elevation, right? These equations aren't going to give me a negative or positive sign. They're always going to give me a positive sign. Boiling point elevation, so it goes up, so 9.6 degrees Celsius. So my boiling point is going to be 109.6. Okay, and I'm out of time. Yes?
So this might be a silly question, but how do you know when to add and subtract?
How do you know whether to add or subtract? That's a great question. So boiling point is boiling point elevation. You always add for boiling point. It's freezing point depression. You always subtract for freezing point.
Okay, thank you.
That's a great, thank you for asking that. Anybody else? All right, you guys have a great weekend. If you have questions, please email me.